In this lesson we will talk about unsupervised learning, and in particular clustering and anomaly detection. So far we have just seen supervised learning techniques, which require a training dataset with labeled samples. So for all the samples we already need to know what is the right label, so that we can train a model and then infer the label of new samples that we have not seen before. But having labeled samples is costly. In particular, in communication networks, numbers are very big. So the number of samples that you can collect is huge. And so labeling all of them is very difficult. So if you are in a controlled experiment in the lab, that's okay. You can more or less easily label your samples because you set up a certain experiment. So you impose already from the beginning the label of your experiments, and so you know the label of your samples. But if you want to apply machine learning in a lively network, in a network that is working in real life, this becomes very difficult. For instance, these are the numbers of Google in just 1 minute. So there are 3 million searches, 100 hours of videos that are uploaded or watched. I don't know, I don't remember. There is 1 million gigabytes of content searched, and a lot of users, a lot of devices. And all these data are not labeled. So asking to the users to label each activity is impossible, of course. So applying supervised learning is sometimes prohibitive in real networks. So we need to find something else. So we need to be able to get insights from the data even if we don't know the labels, okay? And this is why we resort to unsupervised learning. In unsupervised learning, there is no label, let's say, or at least you don't use the label, you don't need a label to construct your model. Your model is just based on observing the dataset, the features, and understand some important information from just observing the features. What is the important information we can get? Well, we can at least group similar samples together. So find similarities. This is possible even if we don't have labels. And this technique of grouping similar samples is called clustering. Or we can try to reduce the amount of information with which we describe the dataset. And this technique is called dimensionality reduction, that we will see in the next lesson. Or we can try to understand what are the samples completely dissimilar to the rest, to the normality of the samples. So we could try to understand which samples are outliers, because they can be anomalies or defects or errors. This technique is called anomaly detection. So today we will see clustering and anomaly detection. In one next class we will also see dimensionality reduction. So let's start with clustering. So as I've already told you, clustering means grouping observations into groups called clusters based on their similarity. Okay, so we just look at the feature vector of each sample. We don't use labels. So clustering is an exploratory technique. Okay, so it's not an inference or a prediction technique, it's just an exploration technique. We explore our data through clustering. Let's give some example of application of clustering. Suppose you're an e-commerce website, okay? So you have a set of users, they are not labeled, but they performed a certain type of, they bought a certain type of articles, they bought a certain number of articles per month, etc. So even if you don't have labels, you can discover similar profiles. So you can group together your users in order to target a good advertisement campaign for each profile of user. this is one application. So for instance, here we are representing just two features in this case. For instance, this is the price sensitivity score, this is the brand loyalty score, so how much these users are loyal to a certain brand. And we can see that all these users are similar, this green, all the black ones as well, etc. So we can just craft one advertisement campaign for the green users, one for the that are not loyal but they are sensitive to prices, so we can just propose cheap articles, etc. So you see, we don't have any label to the users, but we can still do some informed action based on just the observation of features. Another application is when you receive online data, so a continuous flow of data, and you want to understand some events based on this. Let's take the example of Waze. Waze is a popular navigation application which understands, based on collected data from users that installed this application, it understands where there are congestion events or accidents and this sort of things. So not all the users are labeling events when they are driving, okay? But still, just by clustering GPS positions, similar GPS positions, Waze can infer that if there is a big group of users, of user positions that are close enough, then this may likely be an accident or a congestion event. Okay, so through clustering, again, without any label, we can understand if some event is going on. There are different techniques to perform clustering. The simplest one is k-means, and we will see these k-means here. So in k-means, we have first to establish this k, the number of clusters we want to have, and we have to establish this in a priori. This is a hyperparameter. Then we define for each cluster a centroid, which is the mean of all the samples of that cluster. So it's a sort of barycenter. For instance, if we consider this blue cluster here, this point I'm pointing at is a centroid. Okay, then we can compute for each cluster the within cluster variation. That is a sort of measure of compactness of that cluster. In fact, it is the average of the distance between each point and its centroid. So for instance, in this case, the within cluster variation of these three clusters is more or less the same, because the average distance between each point, each sample, and the relative centroid is more or less the same. Within cluster variation is also called inertia by some other authors. So I may use these two terms interchangeably. Observe that to define the within cluster variation, we need to use a distance metric. Usually this distance is just the Euclidean distance between points. So observe that to perform good clustering, you need first to scale your dataset, because when you compute Euclidean distance, if you don't scale, the features with higher values will predominate in calculating the distances. And so you would cancel out the features with smallest value, because they will not actually appear in the distance expression. So first, scale your dataset before performing clustering. So to have a good clustering, we would like to have compact clusters, like these ones here. So we would like to minimize the within cluster variation of each cluster. Okay? Or in other words, we want to minimize the sum of all the within cluster variation. So this is our objective function. So our goal is to find a partition, a division of points, a partition of points, which minimizes this quantity. Intuitively, to do so, we have to, if we have a certain set of centroids, each point should be assigned to the closest centroid, of course. So it doesn't, if I'm pointing at this point here in the screen, it doesn't make sense to associate it to the centroid of the green cluster, okay? You associate it to the centroid of the blue cluster. So let's see now how key-means algorithm works. So the key-means algorithm is meant to decide two things. What are the centroids and what are the clusters around the centroids? So let's see how it works. So first we start with the entire data set without any cluster already. And we suppose k is equal to, okay, we want two clusters. We initialize two centroids randomly, this blue one and this red one. Then in B, we assign each point to the closest of the two centroids. So we will have all this blue cluster here that is closest to the blue centroid, and this red cluster here. Now the clusters are these ones, and so we can recompute the centroids of these clusters. So the centroid of the blue cluster becomes this one, and the centroid of the red cluster becomes this one. Now the centroids changed, so we can reassign points to them, because the closest point to the blue centroid are this one, while the closest points to the red centroids are these ones. Now the clusters changed, so again we should recompute the centroids of these two new clusters, and we do this like this. Now the centroids changed, and we have to reassign points to the closest centroid. You see that there's not much difference between this clustering and this clustering here, because of course after some iteration you will converge. So you will have just minimal movement of centroids and minimal changes in assignment of points to centroids. So at the end you will converge toward a final clustering. And in this case, these are the two clusters we have found. Observe that everything depends on the initial centroids here. So if we change these random initial centroids, we would end up with different clusters. Okay? So how do we initialize centroids? Well, there is no guidance. The only thing you can do is that you repeat the clustering algorithm many times, at least 20 or at least 10, by every time choosing different initialized centroids. And so at the end you will have 20 clusterings, and you will choose the one for using a certain criterion. For example, you can choose the one which minimizes the within variation, within cluster variation. So you will choose the one which minimizes this W. That is actually this one. Okay, so everything works, but we have to decide in advance what is the key. So in the example that I gave you before, okay, it is quite intuitive to see that a good key could be 2 in this case. But there are more difficult cases where it is not easy to decide what is the right key. For example, here, we don't know if key should be equal to 2 or to 3. Moreover, most of the times you don't have a bivariate dataset with just 2 features. You have 100 features or 20 features, so you cannot visualize your points. So you need some criterion to choose key in these difficult cases. So there are techniques that we will not see, but you're free to explore them and to apply to your dataset that choose this optimal key for you. For instance, hierarchical clustering, that however is not very scalable, or dbScan, which instead is quite efficient. But we will not see them. It's up to you to explore them. So for lack of time, let's keep hierarchical clustering. And so let's stick with k-means clustering. So one important hyperparameter is this key. Another important hyperparameter, and so another important hyperparameter is also the distance measure that you would use. And this is not easy to choose because you have different features of different types. You may have numerical features like price, size of your articles, or qualitative features, categorical features, like the brand, the fabric, the color. So choosing the right measure is not easy. You have different types. For instance, you have a Euclidean distance or Manhattan distance or Minkowski distance, which is a generalization of the previous two, and many others. So how do you choose your distance? Well, the first thing is by intuition. If you know your data set, you can understand which features, which distance is more relevant. And as usual in data science, it's also a matter of trials and errors. So you try different distance measures and then you judge what is the cluster that is more satisfying for you. So how do you judge if clustering is satisfying or not? You need some metrics, some performance metric. We have already seen one of them, which is the global within cluster variation, this W, which again, I repeat, is the distance between each point of a cluster and the centroid. So it's the average distance between each point and the centroid. So you can have a within cluster variation of this cluster, then of this cluster, then of this cluster, and then we compute the sum of the within cluster variation to have the total W. But observe that this measure just computes how close are points to the relative centroid. But at the same time, we would also like to have separated clusters. So we would like to have points of one cluster to be as far as possible from the points of the other clusters. So we would like to partition points in order to have very well separated clusters. And the within cluster variation doesn't give us a judgment on this. So we more often resort to another metric that is called silhouette. So let's see how it works. First, we compute the silhouette for each sample, okay? And the silhouette is this B minus A divided by the maximum between A and B. Let's see what is the A. A is the average distance between X and all other elements of its cluster. So if we take, for instance, this sample here, so we need to compute the distance with all the points of its cluster. So the distance between this close point, this other point, this other point, this other point, this other point, etc. And then we compute the average. This is what we obtain is the AX of this point X here. Then BX is instead the average distance between this point and all the points of the second closer cluster. So if we consider this X, the second closest cluster is this black one. So we compute the distance between the sample and all the points of this cluster. And we compute the average. So in other words, A is a measure of similarity of a sample with its cluster. And B is a measure of distance between the sample and other cluster. Then we divide it by the maximum between A and B to be sure that the silhouette will be comprised between -1 and 1. So a good value of silhouette is close to 1, because this would mean that B is high, so the point is, this is B, okay? The point is on average very far from the other cluster, and A is small, so the point is on average close to the points of its own cluster. So we would like to have S as high as possible. We can plot in Python a silhouette analysis plot, which looks like this. So here each line corresponds to a sample, okay? So, and each line, the length of each line corresponds to the silhouette of that sample. So already we can see that by observing the height of each sample, of each cluster, sorry, we can understand how big are the clusters. So in this case, the green cluster is way smaller than the black cluster. And also, we can see that the silhouette of the green cluster is, of the samples of the green cluster, is more or less better than the silhouette of this second cluster here. And we can also plot this line, which is the average silhouette score for all the samples of the dataset. Okay, so we would like to have this average silhouette score as big as possible. So again, I repeat, we have the silhouette score of each sample, and then the average silhouette score of the entire dataset, and we would like to maximize this. So in this example, we have tried two values of k equal to 2 clusters and k equal to 3 clusters. So which one should we prefer? Well, if we look at the average silhouette score, we see that in the first case it is 0.7, in the other case is 0.6. So we should prefer k equal 2 as clusters. Okay, so one thing you could do to choose k is to repeat k-means algorithm many times with different values of k, and then choose the one which maximizes the average silhouette score. In this case, for example, we would have chosen k, and we will do this in our code. Observe that k-means clustering is limited because it is based on the Euclidean distance between a sample and the centroid. I don't remember how I indicated the centroid, whatever. So it is only able to recognize spherical clusters like this. But if you are confronted now with a more complex data set, for example, this one on the left, here we have clusters with a strange shape, let's say. We have this cluster that is more or less spherical, but this cluster, we see clearly that there is a similarity between these users, that they are members of the same family, let's say, these samples here, but the shape is not spherical. So if you run k-means clustering on these data sets, you would obtain something like, for instance, with k equal 2, I think you would obtain something like 1 and 2 clusters, something like that, which doesn't correspond to the real similarity we observe in the dataset. So when you have complex dataset, you shouldn't use k-means clustering, you should use, for instance, dbScan or other techniques. Building on unsupervised techniques like k-means clustering, for instance, we can create anomaly detectors. So we will see how to create one based on k-means clustering and also other techniques based on neural networks and on extra trees. First, we have to define what is an anomaly. Anomaly is a sample that is not normal. Okay? So that is an outlier. In other words, this sample is dissimilar from the rest of our dataset. The causes could be either this sample is denotes an intruder that is trying to connect to our system and to attack it, or a fraud. We will see in our code an application to credit card transaction fraud detections. Or if you are collecting measures from sensors, an anomaly could be a strange measurement that could be too high or too low, and this could be due to just errors in the sensor, some battery of the sensor that is starting to work improperly, or you can have false damages or accidents, unpredictable events. Or you can have also samples that are very dissimilar with the rest, with respect to the rest of the dataset, but actually they are normal. Okay? So this can also happen. This is why anomaly detection is a difficult problem. Distinguishing a real anomaly by a sample that looks dissimilar but actually is not a defect, nor an attack, nor a fraud, is a difficult problem. So by intuition, we will consider anomaly any sample that looks like these figures here. Here we have a signal, okay, so we have a time series. So some measurement, say it is an electrical signal or whatever, a sensor measurement over the time. And we see that there is a clear trend, and we also see some measurements that are somewhat strange. They detach completely from the rest of the measurements. Well, we will consider these points as anomalous. Another example is on the right. Here we have different clusters. Maybe this is the result of k-means clustering. And we see that there are some samples, these stars here, that are far from the centroid with respect to the other samples. So these are also likely to be anomalous. You have different methods to construct an anomaly detector. The first one is supervised method, where you have a training dataset that is also labeled. So you have many samples, and for each sample you know if it is normal, anomalous, and you can also have different categories of anomalies. You can have label attack number 1, attack number 2, or defect, or sensor error, etc. So you can also have different categories of anomalies. And so to do anomaly detection in this case, you just run classificators. Of course, the limit of this method is that you need labels in order to create your model. So you need at least a training set for which you know the anomalous and the normal samples. Another approach instead is based on unsupervised methods that we will mostly focus on. And here we will see three methods based on clustering, isolation forests, and neural networks. Before talking about these methods, let's start with a concrete example. And let's talk about insider threats. The most difficult attacks to discover are the ones that come not from some people outside your organization, but from the employees of your own organization. And these kind of attacks are very frequent in computer systems, and maybe the most famous was the one from Edward Snowden, who copied and leaked highly classified information from the National Security Agency in 2013, when he was a Central Intelligence employee. So, one question is, can we automatically discover if some of our employees is starting some strange activities that are different from the normal ones he should do? Well, there is a lot of research on this and a lot of work, and also a lot of production systems that are available you can buy for your organization. So one way to do it is to log all the activities of all the users, and so that you have a set of samples that looks like this. So each sample represents the activity of one person over a time window, say 1 hour or half an hour or 1 day, etc. And each sample has the following features: the role of the person, whether he is a chef, a manager, an intern, the department, the project, and then, importantly, the number of files open, number of files written, copies on USB devices, number of emails sent, etc. So, if you see that in a certain time window, an employee is copying more files to USB devices than the rest of the employees in the same department or in the same kind of project, then you can be suspectful and you can raise an alarm. So, if such system was working in the National Security Agency, maybe Snowden wouldn't be successful in leaking all this very secret information from the military activities of US. Okay? I let you choose if this would have been a good thing to avoid these leaks of information or not. This is more a political matter. So I'm sure that some insider anomaly detection was active in National Security Agency, but it was clearly not working properly. Okay? So I let you read, if you're interested, these papers here for more details on this kind of problem. Now let's go directly to the technique to implement anomaly detection. And we will start using k-means. So we have talked about k-means clustering, okay? So assume you have a certain data set, you want to understand what are the anomalous samples. You first run k-means k-means clustering. Then you associate to each sample a score. A score is the distance of that sample with respect to its centroid. So it's not the silhouette score, it's a completely another thing, okay? It's the score of this point here that I'm pointing at is its distance from the centroid. Of course, the smaller the distance to the centroid, the more normal is the point. Okay, so anomalies are points whose distance is more than a certain threshold that we usually call tau. So if we establish a certain threshold tau, then all the samples that fall outside this radius around each centroid is considered an anomaly. In addition to this, you may also want to consider anomalous samples of clusters that are too small. So if you run k-means square and you have 1 million points in one cluster, 2 million in another cluster, and 3 points in the third cluster, maybe these 3 points could also be anomalous because they are very different from most of your dataset. So to judge the quality of the anomaly detection method, you use different metrics. Let's first observe precision and recall. So first, imagine all your samples are represented in this square here. And imagine here on the left we have all the anomalies, all the true anomalies. Okay, and on the right we have all the normal points. We say that the anomalies are the positives, while the normal points are the negatives. Now, we define the true positives, the number of anomalies that are correctly classified by our detector as anomaly. So, this point is a true positive because our detector said positive, anomaly, and it was actually an anomaly. The false negatives, instead, are points for which our detector said negative, so normal point, but the point was actually an anomaly. Let's go on the right. False positives or false alarms are samples which our detector recognized as anomalies, but they were actually normal points. So our detector raised an alarm, but it was actually not needed. And true negatives are instead normal points that our detector recognized as normal points. So in this case, the detector was correct. Now that we have defined all the possible points, we can then compute precision and recall. Let's start with recall. Recall is true positive divided by all the anomalies we have. So the recall is, in other terms, the percentage of anomalies that our detector was able to find. What is the precision instead? It is true positives divided by all this circle here. The circle represents the alarms. So actually precision is the percentage of raised alarms that were truly anomalies. So I repeat, the precision is the fraction of alarms that were actually anomalies. So as you can guess, we would like to have high recall and high precision, because we would like to have a detector that is able to find as many anomalies as possible, and a detector that is precise, meaning that if it says this is an anomaly, we want that point to be actual anomaly. We don't want a detector that is very imprecise, that says for many points this is an anomaly and then it is actually not. So recall and precision are both important. Okay, recall is easy to understand why it is important, because we don't want to miss any anomalies, because anomalies are dangerous. And precision is important because if you are a system administrator and you receive a lot of alarms, and so every time you have to check what is going on, what is the event that has been raising an alarm, you will waste a lot of time. So if most of these alarms are false alarms, you will just waste your time in checking for anomalies that don't exist. And even worse, if you receive too many imprecise alarms, wrong alarms, false alarms, you will start to ignore your detector. Okay, so at the end you will not pay attention to it, because most of the time it was wrong and it made you waste your time. So precision and recall should both be high, but there is a trade-off between the two. So most of the time, if you want to increase the recall, you have to decrease the precision. And this can be understood easily if we consider the anomaly detector we constructed in the previous slide. That was k-means clustering with a certain threshold tau. All the points that fall outside radius tau are considered anomalous. So if this tau is very big, suppose this tau is like this, around this centroid, and then this is the tau around the other centroid, this is the tau around the other centroid, you see that you are considering normal all the points. This means that your recall is very low because you are missing a lot of possible anomalies because you included them into this very large tau. But at the same time, your precision is very high because if you say that one point is an anomaly, it means it is very far from the rest of the clusters. And so it is very likely it is actually an anomaly. So very high tau implies a very low recall, so you miss a lot of anomalies, but a very high precision. And so I invite you to reason about what happens when tau is too small. So deciding this hyperparameter tau is a difficult task, and there are methods to help you in this decision. One method is to plot the precision recall curve. So we have defined precision and recall, we can plot them varying different values of tau. So here this point is obtained for a certain value of tau, this other point for a certain other value of tau, etc. So by varying tau, we are actually considering different anomaly detectors. So each point here corresponds to a different anomaly detector, and for each of them you can compute precision and recall and obtain this plot. So how do we plot this curve with the dataset? Well, we will do as follows. So we run k-means clustering, we compute the anomaly score of each sample, that is the distance with respect to the centroids, and then we order the samples from the highest score to the lowest. Okay? And then we say, okay, now we set tau equal to the highest score, and we compute the precision and recall. Then we say we set the threshold equal to the second highest score, and so on and so forth. Like this, you are creating this sort of curve. Observe that when tau is, let's say, infinite, your recall is 0 because all the points will be considered normal, and your precision is 1 because there will be no there will actually be no anomalies given by your detector. While if you decrease your tau, you start to leave out some points that will be recognized as anomalies, so you start to have more recall, but you start to lose precision. Some of the points that you left out will be marked as anomalies, but they may actually be normal. So if tau goes like this, okay, this is the trend you have. Then you have finally, so you have to choose one value. Okay, when you construct an anomaly detector, plotting this curve is just a preliminary operation, but then at the end you have to choose one value of threshold tau, and this is left to your judgment. For instance, you may reason like that. You may say, okay, my computer system is very delicate, is the National Agency of Security of France, so I want a recall at least 0.9, which is already too low, okay, because I want to find 0.9 anomalies, okay, 90% of anomalies. So if I want to obtain this recall, well, I know already for sure, I know already that on average, I will tend to have sort of 0.1 precision, meaning that among all the alarms that I will get, only 10% will be truly anomalies. Or you may say, okay, anomalies are not so severe because maybe I'm measuring the temperature in a room, so I may prefer to have lower recall, so I may want to recognize only 70% of anomalies, and I know that the precision will be sort of 0.3. So among all the alarms, 30% will be true anomalies. Now, suppose you run k-means clustering with different values of k, or you run k-means and other clustering techniques, dbScan or others. So for each of them, you will obtain a different precision recall curve. And can we understand which is better than the other? Well, it is clear that the red curve is way better, because with the red curve, precision recall curve, we may have a like sort of 85% of recall with also a quite high precision. While if we take the blue line, in order to get 85% of recall, we will have a very imprecise detector. So how to summarize this quality of precision recall curves? Well, we use the area under the curve. That is actually the area under the curve. There's no easier way to define it. Okay, so the higher the better. A perfect detector would have area equal to 1 and would correspond to something like that. While a detector, like a sort of baseline detector, would have area under the curve 0.5. In addition to the precision recall curve, you can also use the ROC curve to judge the quality of a certain detection method, and also to guide you in choosing the right threshold tau. ROC means receiver operating characteristic curve, and this time we have on the y-axis the recall, also called true positive rate, and on the x-axis the false positive rate. So the true positive rate or recall is this one. Among all the anomalies, what is the percentage of the ones that we detected? This is the recall. While the false positive rate is among all the normal points, what is the percentage that was classified wrongly as anomaly? Okay, so by repeating a similar procedure as the one that I explained before, you can construct these curves. And suppose you choose a tau that corresponds to this point here. So if you choose this tau, you know that you have 60% of false positive rate, which means that you will classify 60% of normal points as anomalous, and almost 80% of recall. So you will be able to detect almost 80% of the true anomalies. Again, the best curve is the one which has low positive rate and high recall, okay, high true positive rate. So low false positive rate and high true positive rate. So you would like to have a curve like this with a big belly, let's say. And again, you can measure the quality of your curve by measuring the area under the curve. So you have two areas under the curve: the area under the precision recall curve and the area under the rock curve. And you can evaluate both to compare different detection models. Before we proceed, I would like you to be clear about one point. Observe that to compute the true positives, the false positive, etc., we need to know a ground truth. So we need to know in advance what are the true anomalies and the normal points. So you need to have at least some labeled points to understand this. So you may tell me, okay, we said that unsupervised learning doesn't need labels, doesn't need labeled samples. Well, this is partially true. And let's try to understand why it's partially true. So observe that in order to create our anomaly detector, here we didn't choose any label, okay? We just use k-means clustering, just looking at the features, and then we established a certain tau, and we don't look at the labels at all. We just use the labels to judge the quality of our detector. So we use the labels a posteriori, after our model is constructed. Okay? While in supervised learning, we use the labels during training, so to construct our model. Okay? So I repeat this concept. So here we are talking about unsupervised anomaly detection techniques that do not need samples in order to create a model, to construct a model. Do not need labels in order to construct a model. We need labels just to judge their quality a posteriori. Now, we have talked about detection based on k-means clustering. We have also other methods. Another one is called isolation forest. Okay, so this is based on the concept of extra trees that we have explained in the previous lesson. Okay, so suppose you have grown an extra tree, okay, without any label. Okay, so you just have each tree. Where you have in each tree you have different nodes and splitting rules that divide the samples on this node in two other nodes, and so on and so forth, and you have different trees. Now, if you take a certain sample, you can make it traverse the first tree and then the second tree and the other trees, and these trees are fully grown. Okay, so they are grown until the end. And you can observe when a certain sample is isolated. So when a certain sample found itself. An alternative to k-means clustering for anomaly detection is isolation forest. This is based on the concept of extra trees that we have already seen in the previous lecture. But in that case, we were doing supervised learning. So we were using the labels and we were labeling each node with the prevalent class. Here we are in an unsupervised learning context, so we will not use labels. We will just ignore them. And we will just have different trees with random splitting rules, and we will observe how the data set will split among different nodes. But there is no notion of label here. Each tree is fully grown, so the depth is such that at the end we have one sample per node. So these trees are very deep. Now let's take a new sample, okay? And a sample, generic sample. If we let it cross this tree, we can observe when it is isolated. So when it falls into the node in which it is alone. So in this case, the red sample is isolated in the second level. Okay? Then we can repeat it in the second tree, and again the sample is isolated in the second level, and in the third tree the sample is isolated in the first level. You can intuitively understand that the closer the sample is isolated to the root node, the more it is diverse with respect to the rest of the dataset. And so the more likely it is to be an anomaly. So how can we translate this intuition into a formula that then an algorithm can treat? So it is easy. So first we compute the average path of all the trees. Then we compute for each sample, we compute its path length in each of the trees. In this case, the path length is 2 in the first tree. The path length of the red point is 2 in the second tree and 1 in the third tree. Then we compute the average path length across all the trees. And we compute the score as 2 to the power of minus this average path length h divided by p. So the higher the path length, the higher the anomaly score, because this point was isolated far away from the root. This is a visual representation of what we are doing here. So on the right here, this point x is isolated quite soon, quite close to the root, because in this tree we may have done the first split in this way, then maybe this is the second split, and this is the third split. And already this x0 is isolated. So in this case the path length on this tree is 3. While this xi is a normal point, and before isolating it we have to do 1, 2, 3, 4, 5, 6, 7, 8, 9 splits. So we have a lot of splits before finding it alone, and so this is likely to be a normal point. So at the end of the day you end up with a set of scores for all the samples, and so you can compute the receiver operating characteristic curve or the precision recall curve and all these metrics that you have seen in exactly the same way as before. Another idea is to use neural networks for anomaly detection. In particular, we will use the autoencoder, which is a neural network like this. Observe first that it is symmetric. So the input layer and the output layer have the same size. Also, we have these first layers called encoder and these other layers called decoder that are also symmetrical. The number of neurons per layer is symmetrical. And in the center we have few neurons that constitute the latent layer. So in general, the goal of an autoencoder is to imitate the input. So what we expect from an autoencoder is that we give a certain input vector. In this case it is an image, but it can be whatever. And we take the output, and we would like to have this reconstructed output as similar as possible to the input. Observe that this is not trivial, because we are reducing a lot the dimensionality of our data. If we have 100 features in the input, we are condensing them in just 2 neurons in this case. So we are compressing the information. So at the end, I repeat, we would like to have a reconstructed output as similar as possible to the inputs. So the loss function is the difference between the inputs and the reconstructed output. Now, how can we use autoencoders for anomaly detection? Well, we can start with this assumption. Normal points are easy to compress and thus to reconstruct, while anomalous points that are strange are more difficult to reconstruct. So the network will have good reconstruction error, small reconstruction error for all the normal points, while if the reconstruction error is high, then that point is likely to be an anomaly. So actually, with autoencoders, we define the anomaly score as simply the reconstruction error. And then once we have the anomaly score, we can plot again the receiver recall ROC curve, precision recall curves, etc. We will skip it. Now, I just presented 3 methods for anomaly detection, but there are really an infinite number, and this is a synthesis of this, a summary of this, and you see that k-means is used a lot. Decision tree, that it is actually isolation forest, is used also quite a lot, etc. And here I just listed some applications to communication networks or computer systems in general. So if you can read the papers if you're interested, but in this first paper we want to discover insider threats. The second, network intrusions. We want to understand if there are sensors communicating malicious values to drive the system toward undesired states. We may be able to understand wrong measurements or to do predictive maintenance. So you have an industrial plant and you want to predict if a certain part of the plant is going to malfunction. So you can collect measures, and if they are anomalous, you are likely to observe in the future an error, a defect there. And I let you go deeper into this topic if you're interested. At the beginning, I told you that you can do anomaly detection basically using unsupervised learning or supervised learning. Actually, there is also a third way of semi-supervised learning. In this case, you have a training dataset composed of all normal points, and you train a model based on this. For instance, you train an autoencoder to reconstruct well these points that are all normal. And then when a new sample comes, you compute the score. If the score is high, you will classify it as anomaly. Note that in case of unsupervised and semi-supervised learning, we are assuming that anomalies are rare events. So most of the data are normal, we are assuming, and just some of the points are anomalous. Well, this is usually true, but there are cases in which this doesn't hold. For instance, some computer science attacks consist in creating a lot of connections. And so in this case, the anomalous points are actually a lot. And so you cannot use unsupervised or semi-supervised approaches in this case, and you have to resort to classification, to supervised approaches. Another thing it is very important you understand is how to properly tune all the hyperparameters of the anomaly detector. So we have seen that we have a lot of hyperparameters to choose. For instance, if you use anomaly detection with k-means clustering, we have to choose the k. Or if you use iForest, the number of trees. In Autoencoders, the number of layers and of neurons, etc., etc. And also in general, you have to choose this famous threshold tau, above which you will consider samples as anomaly. So how can we choose all these hyperparameters? First, we need a set, okay. Then what we did is that we plotted rock curves and precision recall curves, okay, and we plotted many, maybe changing the number k of our clusters or other hyperparameters, and then finally we choose one of these curves, one of these configurations, and a certain value of tau, which corresponded to a certain precision and recall, or false positive rate, or etc. And then after we fix all these hyperparameters, then we can judge the quality of the anomaly detector, which means we can compute the precision and the recall and the false positive rates, etc. So how shall we do it properly? Well, first, if you have an entire data set, you need, as usual, to divide it into parts, training part and test part. Just ignore the test at the beginning and do all this model selection work only on the training set. Okay? So you plot these curves, you choose the k and the tau just based on the training set. After you have chosen a final model, then you check its precision, its recall, and its false positive rate in the test set. Why it is important? Because if you use the same set, the entire set, to do model selection, that means to find the correct hyperparameters, then it is incorrect to judge the same model on a subset of the same data you have seen before. Because in this case, you would be prone to data leakage. So you would be implicitly using data both for finding the right model and then to judge it. And so you will have good performance, but then in real life, when the model is applied to samples that it has or never seen, the performance would be way poorer. So we will see how to handle it properly in the code. The code to run anomaly detection is in my GitHub in this folder, 6.clustering and anomaly. You will find there 3 notebooks. One for k-means, the other for isolation forests, and the other for autoencoders. They all use one dataset of credit card transactions. So each sample corresponds to a credit card transaction, and some of them are fraudulent. So you have to infer which ones are the frauds so that in real life you could stop these transactions. If you observe the columns of the dataset, they look like that: V1, V2, V3, so there is no clear meaning of these columns. This can happen often in challenges or even in real data science projects, because sometimes the dataset is critical. So in this case, the credit card transactions have been anonymized. So this dataset have been treated in order to obfuscate the information. And so at the end, you have numbers that don't have a clear meaning. This also happens when you participate to a data science challenge and the company that provides the dataset doesn't want to disclose the details of its infrastructure or of its organization. So the dataset is incomprehensible, let's say. But anyways, you have to be able to use these obfuscated columns to understand if one sample is an anomaly, a fraud, or not. So in the first notebook, I use k-means clustering anomaly detector, and you will observe that at the beginning of this notebook, I use the entire dataset. I don't divide in training and test set, but I don't use the labels. So in this first phase, I just want to get what is the best number of k, how many clusters I want, and what is the best number of random initializations of centroids. If you remember, the result of k-means clustering depends on the initial randomly selected centroids. And if you want to have good clustering, you should repeat k-means algorithm many times, every time selecting different random initial centroids, and then you take the result that is the best, okay, with the that gives most compact cluster, which means the within cluster variability is the smallest. So this is what we do here. So we just use x that I scaled before, not y, and we get the clusters. Okay, we get one big cluster and other two clusters that are smaller. Here I'm verifying what is the best value of random initializations, 10 to 100, or here 1000, but I'm checking all the values from 10 to 100 with steps of 10. And I plot, if I'm not wrong, the inertia values, which are actually the within cluster variability. And I take the value which provides the smallest number. Then I use the silhouette diagram to select key in order to maximize the average silhouette score. So for instance, when I use key equal to 3, the silhouette diagram is really bad. First, because the average silhouette score is very low, so it's almost 0, and also we have a big cluster 0, a small cluster 1, and an infinitesimal, let's say, cluster 3, that it is almost not visible. So I try different number of clusters, and finally I see that every time the average silhouette score is very low. So the best choice seems to be k equal 2, which gives a high silhouette number. But I repeat again, I'm not using here any label, I'm just using the features. So this is why I can use the entire dataset. Then I start to do, so I've now finished setting up a good k-means clustering algorithm with the good hyperparameters. Now I will use it for anomaly detection. As you know, to judge the quality of anomaly detection, we measure precision, recall, false positive rate, etc. And to do so, we need to know the ground truth. We need to know the label, whether a certain sample is an anomaly or not. And so this time I will divide the dataset in training and test set, and I will use just the training set to do model selection, so to select the best combination of hyperparameters, and then I will check the result on the test set. So here actually I'm doing this, and I do exactly the same operations with isolation forest. So I will not give you the details. Here notice that here I'm dividing, as I told you, here we are using isolation forest, okay? And here we are dividing training and test set. And we are running isolation forest only on the training set. And then we get the anomaly scores. Okay, they depend on the average path length of each sample. So we have the anomaly score, one per each sample. I programmed this function that you can reuse. We imported in this notebook this function at the beginning, and now we are just using it, where you give the ground truth, you give the anomaly scores that you computed with isolation forest or any other algorithm, and it gives you all these plots: precision recall curve, rock curve, together with the area under the curve in the two cases, and also it plots recall versus precision, changing the threshold. So with these plots, you are now in the condition of choosing the right threshold tau. In fact, yeah, here, if you add this other parameter to the function call, the threshold, you have all these results here. So here I'm saying plot me the precision recall curve, the rock curve, etc., and also plot me the line corresponding to the threshold. In this case, the threshold was minus 0.15. And with this threshold, we have a very high recall, and somewhat higher recall, 0.9, and but also a very low precision that is also printed here. So in this case, we are finding 90% of anomalies, of frauds, but only 1% of the alarms are actual fraud. And also this function gives you the same representation on the rock curve. So here you see that we are obtaining a high recall, as we found before, 0.9, and also a somewhat low false positive rate that is actually 10%, 11%. So this means that 11% of normal transactions will be raising an alert. That is wrong, of course. Okay, so in this notebook I play with different combinations and different hyperparameters of isolation forest, and then I just select one model. Okay, so I'm selecting a certain isolation forest with a certain number of trees, and so I will now check this model on the test set. So I train the model on the test set. So I actually grow the isolation forest on the test set, and then I compute the anomaly scores, and then I use the threshold that I selected before. So I'm saying this vector is 1, which indicates anomaly, if the anomaly score of each sample, of a certain sample, is more than the threshold. So at the end, this y pred is a vector full of 1 or 0. 1 if the sample is considered anomaly by isolation forest, 0 otherwise. And I can compute the precision, the recall, and the false positive rate for this specific model, where the isolation forest hyperparameters have been fixed, as well as the threshold. And this is the final result. So this is the anomaly detector I would put in production in this case. This gives a 82% of recall and a false positive rate of 2%. So you see that these results on the test set may be different than what we had in the training set. And here I'm plotting the confusion matrix. And you see that here I have just 2% of false positive rate. Samples that are normal, but they are classified as anomaly. But you see that overall the confusion matrix doesn't look so bad. In the third notebook, I repeat more or less the same process, but this time I use autoencoders. So I will go directly, so I try different combination of parameters, different architectures, deeper architectures with more layers, or shallower architectures with less layers. I vary the number of neurons. I vary the number of latent layer neurons, because the less neurons we have in the middle, in the latent value layer, the more we are compressing our information. So we have to play with all these parameters. At the end, I select one autoencoder configuration and I go directly to the results, which is this. So at the end, after all my research here in this notebook, I found this result here. Observe that isolation forests, these confusion metrics here, were performing better than autoencoders. So this is a demonstration that not always deep learning or neural networks are better than all the other methods. Okay, so you have to try different ones, and many times tree-based learning is competitive with neural network-based learning. That's all for this lesson. Let's recap what we have done. So we have started by describing unsupervised learning, which is that you don't use any label, so you just look at the features of your samples and you try to get insights from your dataset, just looking at the features. You could do mainly three things by doing so. Clustering, that is grouping together samples that have strong similarities. And we saw one technique, one algorithm called k-means clustering. You can also do dimensionality reduction, which we will see later, and anomaly detection. In anomaly detection in particular, we first constructed an anomaly detector based on k-means clustering. Then we constructed another one based on isolation forests, and the last was based on neural networks, in particular an architecture called Autoencoders.